Merci Loïc pour l'introduction. Et je suis très honoré d'être ici aujourd'hui pour présenter le travail qu'on fait à Soleil. Mon présentation va être un petit peu différente des autres parce que je vais parler en anglais. Je vous excuse par avance pour ça, mais c'est faute de Soleil. C'est faute d'un manque de temps pour la préparation. Donc j'espère que, vu que le sujet de la présentation c'est surtout sur les images, que les images vaut le mot qui va manquer en français. Donc, mais on verra. So, to continue, I'm sorry. Today I'll be talking about new imaging techniques which we can use for the study of ancient materials. And I would like, before beginning, to thank a number of co-workers at Soleil and at the beamline where I work, including Jean-Paul Itier, who is the responsible for the beamline, who will be there all day as well if you would like to discuss. I would like to emphasize that if you do have questions and you'd like to ask in French, or si vous avez des questions en français ou vous avez des choses à discuter, n'hésitez pas, parce que c'est vraiment juste la présentation qui va être donnée en français. So, before I start really in this talk, I'd like to respond a little bit to a point that was made in the previous presentation, that we are scientists who are based on an instrument, and we aren't the ones who are in the field. But we're in a very privileged position, which is that we receive each week not just samples, but we receive also the scientists with their samples to do their experiments. So we're not just doing measurements, we're working together with the researchers to build up something, hopefully, that's very interesting and rewarding. So, what I'll talk about today is the technique of tomography, which we can do at the synchrotron. So I'm going to go briefly through the technique, what it is and how it works. I'll show you where I work at the beamline at Soleil, so I'll present this to you. And then I'm going to illustrate what we do with examples which I've tried to draw from projects where we've worked on ancient materials. So these are things which should be relevant to you and your work, and I hope that they can inspire you with ideas for things that you could do in future or we could do together. And included in that are some new ideas that we're in the process of developing now. So, to start with, tomography, tomo is slice. So the idea of tomography, I think it will probably be discussed in other talks as well, but it's useful to have an introduction. Tomography is 3D viewing, so we cut open our object in a virtual way and we can look inside. So it's a 3D non-destructive imaging technique, and it's essentially equivalent to a medical scanner in a hospital. So this has the advantage for ancient materials of being non-destructive and having minimum sample preparation. So this is really well adapted to unique samples that can't be destroyed. So just to show you how it works, if we have a sample, we don't know what's inside it. What we do is we illuminate that with a beam of X-rays in order to form a 2D image in projection on a detector. So this is like if you break your arm and you go to the hospital and they make an X-ray. What we then do is we rotate the object and we collect a series of projections of the object from different view angles. And from this series of projections, which might be 2,000 projections, we can then reconstruct with an algorithm the interior of the object. So now what we have is a volume where we can virtually open it and we can look inside. So I just show you that quickly on some real data. This is a material science in the modern sense example, but it's a nice, quite a pretty sample. This is a fiber composite tube. So it's a tube woven out of fibers. And what I'll show you is how we take these projections and we smear them back through the object to reconstruct the shape. And so you can see as we add more and more projections, the form of the object becomes apparent. And if we look at a small area, we can see as we add in more and more projections, we can reconstruct even the very fine details and tiny pores and tiny cracks in this object. And all this is done in a non-destructive manner, and these are things which are not visible from the outside. So just to emphasize, the volume, this is one radiographic image, but the data that comes out is three-dimensional. So we really have a volume. We have a series of slices, and so we can open our object and look inside. And of course, we can slice that in any dimension that we want. So now, in this perspective, we really start to see the internal structure of this woven material. So that's the technique. Now, this is a technique which can be performed with many different sources of radiation, so not just with X-rays. It can be done in a hospital or in a laboratory with an X-ray tube. It can be done using neutrons. It can also be done using acoustics or visible light. It can be done with a whole range of techniques. We do it at the synchrotron, and the image just shows a schematic of the SOLEIL synchrotron source. In a synchrotron, we accelerate a beam of electrons to almost to light speed, and we maintain this beam in a ring. And we use it simply as a source of radiation. So we use the X-rays which are emitted from that ring. And that's the source of illumination which is used for us to do our experiments. And so the reason that we do this is because this synchrotron radiation has very special properties. The principal one is that we have very high flux. We have many, many photons when we compare to any other source of X-rays. And in particular, the source is very brilliant. So that means it's very small, it's very collimated. And when we compare using this brilliance measure, a synchrotron is at least 10 to the 8, so 8 orders of magnitude brighter than anything that we would have in a laboratory. We compare on brilliance because it's the measure that favors us the most, but nonetheless, we have a lot of photons to use for our experiments. And this gives us many possibilities in terms of going fast, in terms of going to very high spatial resolution, or in terms of being extremely sensitive because we can use the coherence of this very brilliant beam. So I'm going to explain, I hope, why all of this is important with the examples that I'm going to show you in a minute. So this, in reality, is what the synchrotron looks like. So we're based on the Plateau de Saclay at Saint-Aubin. And so this is our research center. It's a ring which is nearly 350 meters in circumference. And we have about 29 beamlines and many thousands of users who come to do their experiments. The important details here are that it's been in operation progressively since 2006. And what's really important is it's an institution which can be accessed by anybody. So although there are industrial users who pay for access, scientific users are selected on merit. So you write your proposal, and if you have interesting ideas, you'll be invited to come and do your experiment, and that's all you have to worry about. So that's SOLEIL. I'm going to talk a little bit about our little bit, which is Psiché. So this is a plan of the synchrotron. We live in this little part of the ring. So there are 29 different beamlines at the synchrotron, of which 3 will eventually be available for imaging and tomography. We are the first one to be in operation. There will also be a dedicated beamline for imaging experiments, which is called anatomics. And there will be a beamline not only dedicated to imaging, but dedicated to imaging for cultural heritage and ancient materials. So really a beamline that's designed for this community, and that will be called Puma, and that should open soon. So this is us, this is Psiché. Psiché is pressure, structure, and imaging by contrast at high energy. So we're the high energy beamline of SOLEIL. What that means is, with X-rays, the higher the energy, the more we can penetrate into materials. So we can get through large samples in a non-destructive way. So we can measure deep inside artifacts or objects. We do actually two different things, which is important to this talk. We do diffraction for extreme conditions, and we also do tomography for imaging. And although we're designed for contemporary material science, we're not limited to this, and I hope I'll be able to illustrate this. What we are is we're very flexible because we do this combination of techniques, so we are in a very good position to combine things together and to try new things. We're not limited to any one single area of research. This is what it looks like. Just to show you, we have two experimental hutches where we can work. To give you a sense of scale, this is about 20 meters from the entrance to the first hutch to the back. And at this position here, we're about 36 meters, I believe, from the synchrotron. So the ring is up here, around Barthélemy. So if we look at what the instrument actually looks like, this is our tomograph. The sample sits here. We have a rotation stage to rotate it in the beam. And what we have, which is special, is we have a lot of space here. And into this space, we can put a whole load of interesting user experiments. So here are two that really exploit the size and the space that we have. On the left, a group from INRA who work on living plants, and so they come with their vines and they can install these inside. And on the right, we have a first archaeological example, and this is a fossilized bear femur. So these are big, proper cave bones, and we're able to look inside in a non-destructive way and do microscopy on the bone structure with an aim of identifying different species and looking at the eventually to be able to identify species from very small fragments of bone. So that brings me into the examples of how we can use this instrument. So I'm going to go through in three sections. First is regular, what you could call regular tomography, just using the absorption contrast, so how the samples attenuate the beam. The second is phase contrast, which I'll explain. This is something very special to synchrotron radiation. And then we have the new ideas and where we're hoping to go in the future. So this is the first example, and it's one which I'm going to come back to later as well. This is a study with, among other people, with Loic, and with the students Jai Li and Marta Bellato, so based at Ipanema, which is based at the Soleil site. And in this example, we're interested in textiles which are 4,000 or 5,000 years old, which have been preserved because they've been infiltrated by corrosion products from metal artifacts which have corroded. And that's caused them to effectively to be fossilized. And so they've survived when normally they would not. And so we've got some kind of a metal object. And if we look in detail on the surface, we can see these traces of the textile. So this is a little fragment which we studied at the beamline. And now, so we've done a tomography measurement on this. And now I'm just going to show you section by section going through this little object. And so here, if we look, this is layers that are quite close to the surface, and we can see the fiber structures here. You can see all of the individual threads and how it's woven together, and then the structure of the textile. And some of that's visible on the surface, but some of that is really deep inside, buried in the crust. And then as we go through, we see other layers appear. You see this is a very rich structure, and there's a lot to understand in this. And as I say, we can look at this from any orientation. So now I just show you a slice cut through this way. So we can see the fibers in section in the surface. We can see fibers that are buried inside. We can see that there are many different layers. This is not just one material. This is a rather complex system. And these people are interested not just in the fibers, but also in the mechanisms of the corrosion. So they'd like to understand what are the materials, how does this actually happen, what are the mechanisms chemically and in terms of the materials. So this is a first example, and I'm going to come back to that later in the final section. Another example, which is in a way ancient materials, which illustrates some of the possibilities of the technique, is to look at meteorites. And here, this was with a group from the Institut d'Astrophysique Spatiale, and they wanted to study very tiny fragments of meteorite, so we need very high resolution in order to see inside. And so, in this case, we can go down to a resolution better than half a micron, and we can use this to study these tiny fragments of what's called the Paris meteorite, which are only perhaps 40 microns across. But we can look inside this tiny object, which you can't see by the naked eye, and we can see inside it, and we can see many different structures and phases, and there's a lot for these people to understand. So that's what you could call basic tomography. Now, phase contrast is something that for this community, I think especially, has become very important over these years. And what is meant by phase contrast is that when the X-ray beam propagates through the sample, it's partly absorbed, but it's also refracted as light is refracted through a prism. And what that means is that even if there's very weak contrast in the sample, we still see an effect on the detector, especially as we start to increase the distance. So this would be our classic picture that I showed you before. This is now if we start to increase the distance between the source, between the sample and the image plane where we put the detector. And on the right here, I've just got some images that were made from a piece of burnt wood, so pyrolyzed wood. So this is essentially just pure carbon. It hardly absorbs the X-ray beam at all. If we put the detector close, we see almost nothing. There's no contrast at all. Simply by increasing the distance from sample to detector, we see stronger and stronger contrast. And what this means is that something that's invisible becomes visible, and this is what we're interested in. And then what we do is we have special algorithms that exploit these contrasts in order to reconstruct the object. So now I'm very grateful to my colleagues at the ESRF who've provided me with a couple of really beautiful pictures to show to illustrate what you can do using the power of these kind of technique. And so this is from Vincent Fernandez from ID19, which is probably the beamline that's the most famous at the moment or the most successful in terms of investigations on ancient materials. So they've looked at, I think this is a little fossilized egg, I believe, or maybe not. This is where being not the person in the field is a disadvantage. This is, in any case, a very small fossilized nodule of some kind. With a laboratory micro-CT, so a microtomograph, we see that inside there are some fossil remains, and it's possible to separate perhaps a dozen bones. If we take that to the synchrotron in our standard mode, it's better, we see more, but still the picture's very incomplete. Exploiting the phase contrast now, we see a multitude of bones, and there's really everything in here. And separating this out, they can start to work and understand what was here. All of this missing information has been recovered. So this is exciting and this is powerful. So to illustrate that with an example from our work at Soleil, this is another collaboration with Ipanema, with Pierre Guriot, and also with Derek Siviter from Oxford. So these are fossils which are from the Herefordshire Lagerstadt. And now this is a very special, rich fossil site which was a shallow sea which was buried or infiltrated by a volcanic eruption. So it was filled very quickly with volcanic ash, which buried and accreted around many, many organisms that were living in a very rich marine environment. And what happened was, because it was so fast, the soft tissues were preserved remarkably well. And what that manifests itself as today are these nodules, so these rocks. And so the current state of the art was to hit this with a hammer, and it breaks open, and you can see inside little things that are preserved. And you can see them if you cut the rock like that. But what was known was that with a laboratory tomograph, they're invisible because there's just not enough contrast. So the classic way of studying these things was to do destructive serial sectioning. So you take your rock and you polish away layer by layer, and each time you polish away a layer, you take a photo and you go through your fossil layer by layer. And at the end, you stack up your layers and you can produce these really beautiful images which show perfectly what's been preserved, and they show how rich and how important this fossil find is. But you don't have your fossil anymore. It's been reduced to dust and washed away. So it exists at that point only as a digital volume. And this bothered Pierre sufficiently that he went and got a series of these fossils, and we did an experiment on the beamline, exploiting the phase contrast of the synchrotron. And what this means now is that we can see inside these rocks, and we can see everything. We can see the structure, we can see inside the structure, we can see very fine details. So this is the first one. This is a sponge, some sponge organism. And these are just two sections through. You can see even these very fine spines. And on the right, we see a 3D representation based on these data. This is the second one. This is some kind of colonial organism, so like a small coral-type structure. Again, this is our nodule. These are two sections through that little preserved object. And what's fascinating here is that even inside we see details. So there's hope in the future that we could go in even higher resolution and we could actually see if there are things living inside, because there's every chance that they're preserved and the fossil is still existing. We can go back and try again or do it better. So this is really an exciting opportunity. Now, to show you really the limits of what is possible with this kind of technique, I'm again grateful to Vincent Fernandez to show you really what is possible when when you're really an expert, what you can do. So this is an example of a burrow. So it's a fossilized burrow, a ptero. And these are from South Africa. And what they noticed on this piece of fossilized burrow was that there was a little bit of a fossil protruding at one side. And so they took it to the synchrotron and they scanned it at ID19 or ID17 in Grenoble. And this is just a surface rendering. You can see the skull that they identified as an early mammal protruding from the surface of this fossilized burrow. And with the power of this kind of phase contrast tomography, they're able to reveal and to segment all of the details of what's inside. And they were astonished to find that this is what they were expecting. So they found the early mammal that they were expecting. They also found something else. And this is some kind of predatory amphibian. And so this opens a huge number of questions about what are these two animals doing together in this burrow, what's the history, what's the ecosystem, what is the context that leads to this fossil find. And so one of these skeletons is this mammal forerunner. The other, let's bring it back, is this semi-aquatic predator. And they were even able to see that this one had some injuries. it had been crushed or attacked, it had broken ribs, and they could see that these had partially healed. So it was not, they see even this level of detail. And so I won't talk about it more because it's not my subject and I am not the one who can answer really the questions. What I learned from Vincent's slides is that their current hypothesis is that probably the mammal was hibernating and, you know, was semi-dormant, and that this animal was taking advantage of the burrow to recover and to hide and to heal up after whatever accident it had had. But this is obviously work in progress for many different researchers working on many different aspects of this data. There's not just the ensemble, but there's also details like the teeth, which I think someone will talk about later. There's details of the anatomy and it's very, very rich. So that's, I would say, the current state of the art. I want to just show you one or two new ideas which could come to this subject. So for that, I'm going to go back to the example that I showed you at the beginning, looking at the corrosion structures of these corroded artifacts and the preserved textiles. So Jai, who is the PhD student, has been working on this, trying to use these different grey levels in a really quantitative way. So she studied a series of standards and tried to calibrate really the grey level to the density of the material. And by having this calibration, to be able to really identify quantitatively what is this material, what is this material, what is this material, and in this way to be able to understand the mechanisms better. And so with some prior knowledge and some guesswork and some hard work, it's possible to do this, but there is always an ambiguity because we have one grey level, and in fact, we don't know very much about the chemistry. There could be porosity that we don't see. These could be mixtures of materials. There's nothing to say that they're pure. So what we've tried to do is we've tried to add to that using a second diagnostic, which is to use diffraction, because this is something that we can do on our beamline. So diffraction gives you information on crystals. So we put in a beam of radiation, we get out some kind of spectrum, and these peaks in the spectrum correspond to the crystalline structure. So we can use them to identify what materials are present, and we can also use them to reveal the state of the material, if it's under pressure or under strain. At the same time, there are other mechanisms that we can exploit, like fluorescence, spectroscopy, which reveal other aspects of the material. So in this case that I'm showing you, we're using diffraction to look at the phases which are present. On the beamline, it looks like this. This is now a picture taken with a different experiment, but the sample is in here. We have the detector here for the imaging part of the experiment. So this is for the tomography. So that's the beam going through the sample, making the image. And we also extract a beam to look at this diffracted signal using this detector here. So, just to give a first demonstration of what we can do in this way, I've applied it to a test sample in order to test the concept and to produce some pretty pictures to demonstrate that it works. So here I've got different capillaries with different powders inside, and I've made a grid of points where I've extracted the signal using diffraction. And so different peaks correspond to different crystalline phases. And we can build up a map of all these points, of all of these different components. And we can overlay all of that. And now we can see that we've got 2 capillaries containing magnesium oxide, 2 containing copper, 1 containing gold, 1 with something else that we haven't shown here, and lots which are empty. So this shows that the concept works. So now the idea was to apply that concept to these ancient samples. And so we do like this. We make a tomogram, we make an image, and now we can add to that image, we can add our diffraction information. So we define a grid of points like this, and we go to each of these points, and we make a diffraction measurement. So we extract a spectrum at each point, and if we just plot out the spectra, we can see now there are different peaks which we assign to different phases, and we can see the intensities vary as we go through our scan. And so we can look at the variation of intensity of each phase at each position. And if we take that data and we overlay it onto our tomography, we can produce something that looks like this. So now we see the section of our sample. We can see the different layers that were identified by the different gray levels. We can see the fibers in the surface. And now we can look at what crystalline phases correspond. So we see now that the core of the sample is, in fact, nantochite, it's copper chloride. We can see that the densest phase which is present is not copper, which is one of the things that we thought at the start. It's actually cuprate copper oxide. And we can see other phases which are present in the fibers, in the corrosion layer, including acatamite, but there are also other phases present. And something that's nice, which you can't see on this screen, is the support here is actually a polymer, and we pick up very nicely the polymer as well. So we really add a richness to the tomography data that we acquired to start with. And this is really the power of the technique, is that we can make our tomography of the whole object relatively quickly, and then we can go into the interesting points, and we can see in more detail what is really present. So one other potential future perspective which I'd like to mention before I finish is to go to even higher resolutions, and this will eventually be possible on the beamline anatomics, which will have a transmission X-ray microscope. And in this case, the experimental scheme is similar, but we use X-ray objectives to magnify the X-ray image. And like this, we can do everything that we've done so far, but we can push the resolution down to the order of 50 nanometers. And because we've got the synchrotron as this brilliant source of X-rays, we can still get a good signal from such a tiny volume in a reasonable time. So this, I think, will also be an exciting thing for the future. So that brings me to the end. And so I hope I didn't bore you too much. I hope that I convince you that we've got a very powerful tool to bring to your research, and that the message that we can combine this with other diagnostics to make a richer picture is also something interesting. So if you do have questions, do please get in touch to discuss. And I would just say one more thing, which is that I've talked about essentially 3 of the instruments at Soleil. There are 26 more which also do interesting things, and I would invite you to see, because there's other things out there which are also interesting for you. So with that, I'd say thank you.
Merci beaucoup. Thank you very much. Donc on s'était laissé un petit peu de temps pour prendre des questions sur les 3 interventions, et quitte à mordre un petit peu effectivement sur la pause café, est-ce qu'il y a des questions? Voilà, en commençant peut-être sur la présentation de Jean-Denis Vigne. Mais, Une question de Denis Gracias.
Oui, juste, Andrew, est-ce que tu peux nous dire quelques mots sur les dégradations des échantillons en fonction du flux de rayons X, qui est quand même très intense?
Donc, je peux parler ici? Oui, OK. Donc, la question, c'est sur la dégradation par rayons X. C'est vrai que ça peut être important, et c'est quelque chose qui doit être considéré dans la conception de la manip, de l'expérience. En général, avec la tomographie, on ne voit pas de dégâts dans l'échantillon. Ça, c'est typique. On a vu, avec la diffraction, où on met un faisceau qui est très intense, des changements dans les échantillons, et donc c'est quelque chose qui doit être testé en amont et pris en compte dans la méthodologie de l'expérience. Et ça, c'est quelque chose aussi qui devient plus qu'on pousse vers la haute résolution, plus le flux doit être concentré et plus il faut qu'on fasse attention à ça.
Est-ce qu'il y a une autre question ? Oui.
Oui, j'étais absolument émerveillé par tout ce que nous avons vu, y compris bien sûr par la tomographie et Soleil, le synchrotron, puisque nous en sommes encore loin, nous avançons vers la machine à ne plus fouiller, c'est-à-dire arriver à regarder non seulement à l'intérieur des matériaux et des objets de dimension réduite, mais un jour à regarder de cette manière la totalité d'un site. Donc, naturellement, c'est quelque chose qui est totalement utopique à l'heure actuelle. Mes questions seront plutôt pour Jean-Denis et pour Anne Le Herf. Et il m'a semblé, bon, immédiatement, moi, je ne suis pas du tout spécialiste, je suis qu'un archéologue simple, mais un problème m'est apparu immédiatement qui est celui du local et du général. Alors, à partir de quel moment est-ce que l'on peut penser que l'on généralise à l'entière Eurasie ? En effet, il est toujours possible, et je vois Jean-Denis qui hoche la tête, c'est tout à fait ça, il est toujours possible de tracer des flèches à travers les continents. Néanmoins, on peut accumuler les données et les analyses, et à un certain point, les méthodes évoluant, c'est aussi quelque chose d'important, il devient peut-être intéressant de s'interroger sur les capacités que nous avons à conceptualiser cette évolution et notre capacité immédiatement évidente pour tous à généraliser. Et l'autre question qui me vient aussi, qui est plutôt pour Anne Le Herf, c'est toujours celle de la généralisation, puisque tout devient un document, tout devient un vestige à l'heure actuelle. Autrefois, l'on raisonnait simplement en se demandant, sans s'interroger, à partir d'une matrice dans laquelle on trouvait des choses. Or, maintenant, tout peut être sujet à analyse, à diverses analyses. Donc, en effet, comment arriver à pouvoir les archiver ? Il me vient à l'esprit, bien sûr, tout ce qui concerne les grandes archives de la météorologie mondiale. Qu'est-ce qu'on en fait pour le futur ? Comment peut-on les traiter, les garder, sachant que là aussi les outils évoluent sans cesse. Donc pour cette archéologie qui commence avec la paléontologie et qui ne... Bon, il y aurait beaucoup à dire également, qui ne doit pas être non plus coupé du texte et du discours. Comment, à l'heure actuelle, est-il possible d'arriver à votre avis, à répondre à cette question, donc de tout prendre en compte, tout en arrivant à faire des tris, sachant qu'automatiquement les tris se font généralement par de grands malheurs ou des catastrophes. C'est une question d'archives. Je ne veux pas terminer là-dessus.
Merci. Donc la première partie pour Jean-Denis.
Alors, oui, je vais essayer de répondre brièvement. Alors déjà, ne plus fouiller, ça serait terrible. Non, mais c'est pas simplement parce que c'est un plaisir intellectuel, c'est une aventure intellectuelle et humaine extraordinaire, mais c'est pas surtout pour ça. C'est parce qu'on a besoin des objets et on a besoin de les analyser. Et quand je dis des objets, c'est au sens large, évidemment, hein, on l'a vu. Mais l'objet, c'est aussi la relation stratigraphique entre deux unités, etc. Donc je pense que la fouille, elle a encore de belles heures devant elle. Peut-être qu'il faut la faire autrement, justement, et de manière plus raisonnée, plus parcimonieuse et plus ciblée. Sur la deuxième question, ta deuxième question, en fait, c'est la question de l'échantillonnage archéologique, au fond. Hein. On a des points sur une carte. Et ben ça, c'est la grande faiblesse, c'est la grande tristesse de l'archéologie, c'est qu'on ne construit des scénarios qu'à partir des points qu'on a, et cet échantillonnage n'est évidemment pas aléatoire. Il est profondément lié à l'histoire taphonomique des sites, des régions, et puis il est profondément lié aussi à l'histoire sociologique de la profession et à l'histoire politique. On en a de très tristes exemples depuis pas mal d'années. Donc c'est vrai qu'on est obligé de travailler avec cet échantillonnage totalement contraint finalement et pas du tout aléatoire. Alors en revanche, tracer des flèches tracer des flèches, c'est pas, ça n'est qu'un scénario, une hypothèse proposée, tant qu'on n'a pas établi des liens de proximité, c'est-à-dire des distances, je dirais presque géométriques, entre les objets qu'on étudie, et qu'on ne les a pas organisés sur une échelle chronologique. Parce que ce qui permet effectivement de tracer des flèches, alors il faut bien distinguer effectivement des flèches qui sont des hypothèses sur lesquelles on va travailler, alors qu'il en existe d'autres, mais des flèches qui sont effectivement, je dirais pas démontrées, parce que ça serait difficile d'aller jusque-là, et puis on sait bien qu'on n'est pas dans des sciences exactes pour le coup, mais des flèches qui sont soutenues par un lien. Et je pense en particulier au lien phylogénétique. C'est là que l'analyse de forme extrêmement fine ou les molécules fossiles créent ce lien. Et ce lien n'a de valeur que s'il est orienté chronologiquement, évidemment. Donc c'est ce croisement dont j'ai montré, je pense, plusieurs exemples, entre lien de parenté, phylogénie et chronologie, qui permet d'aller un tout petit peu plus loin que le scénario, ou du moins de tester ce scénario.
Anne-Laure, pour la deuxième partie de la question.
Alors, sur la question du tri, c'est une question évidemment qui est liée à l'évolution de la documentation. Pour que cette question du tri soit un tri réfléchi plutôt qu'un tri subi et aléatoire, qui est l'essentiel aujourd'hui. Je pense que c'est effectivement la question de l'évolution qui est double de la documentation archéologique, à la fois changement de nature et puis changement quantitatif, puisque c'est complètement exponentiel aujourd'hui. Donc c'est un vrai questionnement, c'est un vrai sujet auquel les archéologues sont confrontés, cette question double. Et c'est pour ça que la réflexion, me semble-t-il, doit aller dans le sens de considérer cette documentation archéologique dans ses évolutions et sa dynamique comme une archive au sens plein, avec les réflexions qui accompagnent ce que peut être une archive. Alors la législation française s'est emparée du sujet dans la dernière législation et dans les derniers décrets, dans les derniers textes, pour que justement il y ait une possibilité, parce qu'aujourd'hui ça n'existe pas dans la loi française de pouvoir trier le mobilier archéologique, on n'est pas censé trier, mais ça arrive de toute façon. Donc il vaut mieux qu'il y ait un encadrement de cette pratique, une possibilité, mais cette possibilité ne doit pas simplement rester au niveau législatif. C'est évident qu'il faut que les scientifiques s'emparent de cette question-là pour savoir sur quels critères on peut agir, quelles modalités, avec quelle finalité, en essayant de voir ce que je disais tout à l'heure, c'est-à-dire que qu'est-ce qu'on va garder, qu'est-ce qu'on va exclure, en essayant d'anticiper sur ce problème des méthodes d'exploitation de demain, avec toute l'inconnu qui est qu'on n'a pas toutes les méthodes de demain. Donc il faut prendre des risques de manière responsable, c'est pour ça que j'ai utilisé le mot, mais il faut en tout cas affronter le sujet directement, ça c'est absolument certain.
Jean Politier.
Oui, juste toujours pour cette histoire de tri, on a vu les très belles images qu'a montré Andy sur des échantillons, mais il est évident que, moi j'ai vu la photo où tu entassais un certain nombre de coupelles et de choses comme ça, donc le nombre d'objets potentiellement qu'on pourrait étudier en rayonnement synchrotron est tellement gigantesque que se pose encore plus la question de tri, de savoir lequel on va emmener sur le synchrotron ou sur n'importe quelle technique de caractérisation. Pourquoi celui-là et pas celui d'à côté, sachant que l'échantillon le plus rare n'est pas forcément le plus intéressant, donc on peut aussi se poser des questions derrière, et c'est pour ça qu'il faut qu'il y ait un contexte extrêmement fort autour des échantillons qu'on amène sur les techniques de caractérisation, qui ne peut pas être fait par les gens des techniques de caractérisation, mais qui ne peut être fait qu'en amont par les archéologues, paléontologues, et ainsi de suite, parce qu'il faut un contexte qui justifie qu'on aille plus loin. En gros, nous, on va essayer de répondre à une question qui est posée, mais si vous connaissez déjà la réponse à la question, ce n'est pas la peine de venir sur le synchrotron, et si vous ne la connaissez pas, là, il faut vraiment essayer de voir quel est l'objet qui va permettre d'aller plus près de la réponse. C'est ça que je voulais commenter.
C'est clair, c'est pour ça que je parlais d'échange et de langage, parce que du côté il faut des problématiques historiques en amont des analyses, ça c'est évident, et du côté des archéologues, toute la difficulté parfois est de savoir quel type de questions on va pouvoir poser. On a des problématiques historiques, mais avec quelle machine va-t-on pouvoir avoir des éléments de réponse? Ça, c'est pas forcément évident de l'avoir du côté des archéologues. Voilà.
Et un complément de Jean-Denis Vigne.
Très brièvement, ce que tu décris, Jean-Paul, nous y sommes confrontés tous les jours lorsqu'il s'agit de choisir quel site on va fouiller en fonction de quelles questions on se pose. Donc c'est en fait un emboîtement, c'est une chaîne, et c'est une chaîne de décisions qui met en jeu des compétences complémentaires de plus en plus nombreuses et de plus en plus distantes quand on prend les deux extrêmes. Ce qui est, je crois, un vrai problème, comme l'a bien dit Anne, c'est d'arriver justement à conserver ce lien entre le site et des analyses qui ne doivent pas devenir réductionnistes, malgré tout.
Oui, Étienne Anheim.
Oui, c'était un complément à la discussion sur la question du tri, parce que je pense que c'est une discussion qui est tout à fait transversale à un certain nombre de nos disciplines et sur lesquelles les questions archéologiques rejoignent directement, en particulier les questions archivistiques, depuis la loi de 1979 et le travail qu'ont développé un certain nombre de services des archives. La question du tri, y compris accompagnée par d'un côté des professionnels de l'archive, par des historiens et par des gens qui travaillent sur les algorithmes, par exemple, pour savoir quel échantillonnage on va pouvoir conserver de séries extrêmement massives, est un domaine sur lequel il y a eu des travaux interdisciplinaires tout à fait intéressants et qui aujourd'hui se sont développés dans la direction des big data et du tri des archives nativement numériques. Et en fait, les problématiques archéologiques ici rejoignent très directement, je pense, ces interrogations, et ça sera intéressant aussi à l'avenir sur ces questions d'arriver à les rejoindre de manière plus étroite.
Est-ce qu'il y a... Oui.
Oui. Cette question, c'est celle de ce qu'on appelle le big data, où on est aujourd'hui déjà confronté à des masses qui dépassent notre capacité de traitement ou notre capacité même de compréhension. Il y a des pays qui prennent, des pays à fort patrimoine archéologique, qui prennent la question en amont, c'est-à-dire qu'ils font des réserves archéologiques. Il y a des zones dans lesquelles on ne fouillera pas, parce que c'est un site de plus de telle ou telle nature. Ces pays le font et ça repose généralement, ça repose toujours, sur une analyse préalable qui est faite du site. On a maintenant des techniques d'approche à distance qui permettent du lidar jusqu'à la résistivité. On sait absolument tout faire. Et on a des sites que des pays, je pense en particulier à des pays d'Amérique latine et d'Amérique centrale, décident de préserver. Donc on ne va pas y toucher. Alors ça résout radicalement la question du stockage. Ça ne résout pas la question de l'aspect aléatoire de la connaissance archéologique. Donc on est là dans un tiraillement entre patrimoine et soif de connaissance qui nous réunit tous ici et qui nous anime tous. Ce n'est pas facile à trancher. Et rares sont les autorités qui acceptent de se soumettre à un avis purement scientifique. Parce qu'il y a toujours des avis parasites qui sont sur l'exploitation, la non-exploitation, etc. Et je pense que c'est à mettre dans le catalogue de nos idées à traiter, pas aujourd'hui, mais à garder présent en tête, à éviter que la documentation ne soit surabondante et ne vienne déséquilibrer la connaissance. Ça, c'est un vrai problème que nous connaissons évidemment tous actuellement.
Oui, Anne.
Juste un tout petit mot, parce que la réserve archéologique, on la pratique également aussi en France. Le problème s'est posé de manière évidente avec les développements de l'archéologie préventive, où là, il n'y a pas le choix. On est effectivement, et c'est heureux, donc c'est toute la difficulté, effectivement, sur un bien fondé de faire de l'archéologie préventive, de voir comment ensuite on traite la question.
Prolonger trop et vous voler votre café, d'autant plus que le résultat de la fouille peut se faire attendre. Il y a de pauvres malheureux comme moi qui passent leur vie à expliquer aux collègues que 20 ans c'est un peu long. Donc il faut aussi qu'on ait un résultat, un accès qui justifie, et il y a des législations dans certains pays qui interdisent à la fouille quand la publication n'est pas faite. C'est un peu ce à quoi on est en train de tendre d'ailleurs. Méfiez-vous, collègues.